Like most multi-part problems we've just been looking at, we need to divide this up into certain parts. So we know the bullet's moving at speed vs before the collision. After the collision, we don't know their combined speed, and then we know they slide to rest underneath friction in the final spot. So we can look at this in terms of 1 to 2, we have a collision, and then 2 to 3, we can look at this in terms of energies. So from 1 to 2, we can use momentum. The initial momentum will equal the final momentum of the system, and then we can look at this in terms of kinetic energies to either negative work done by the system or a change in internal energy of the system, depending on if you include the surface, which means you would then use a change in internal energy, or you exclude the surface, which means work would be done by friction. So initially we have the bullet m times vs is equal to the sum of the masses times the speed after the collision. And then we have the kinetic energy of both masses and their speed after the collision. And I'm going to look at this in terms of work done minus the force of friction, so mu k times the normal force times the distance d that it traveled is equal to 0. So looking at this, in order to determine what the initial speed of the bullet is, we would have to solve for the speed after the collision using energies. So I can move the work done by friction to the other side of the equation, which means I would then have 1/2 times the quantity m plus capital M v1 squared is equal to mu k times m plus capital M times g, which would be the normal force, times d. Well, the quantity m plus m will divide out, multiply both sides by 2 and take the square root. I would get 2 mu k g d, and then take the square root of that. And then I could substitute that in, and I would find the speed equal to the quantity m plus m times radical 2 mu k g d, all divided by